Okay, so hi everybody. Here's the link to the live stream. So it's lecture 18. Oh, sorry. Yeah, so it's lecture 18. And today we're gonna talk more about probability, and we're gonna introduce maybe the most important concept in probability, which is conditional probability. And then after that, we're going to introduce a related concept called independence. Or actually, after that, we're going to introduce this related concept called independence. And finally, we're going to talk about a very useful, but simple formula related for conditional probability called Bayes' rule, which is very important in statistics and in many applications of probability. But first, I want to wrap up this stuff about so by the way, this Bayes rule is 7.3, and this other stuff is section 7.2. So first, I want to wrap up the Monty Hall problem discussion we were having last time. So let's recall the basic notions. So in the last lecture, we learned about the very basic notions of probability, which were the notion of an experiment, and then a set of outcomes of an experiment. Sorry. And then the set of all outcomes, which was very important, which we call the sample space, S. And then the probability distribution, which is just a non-negative function on the sample space, such that the sum of the probabilities adds up to 1. And then we had the notion of an event, which is simply a subset of the sample space. And then finally, the probability of an event, which is the sum of the probabilities of the points, the outcomes that are elements of that event. So these are the basic notions. And using this, we wanted to analyze this somewhat complicated situation of a game show, which I've saved my slides from the last lecture, so I'll just pull them up again. So let's recall the setup. So there's a game show where there are 3 doors that are closed, and a car is randomly placed behind one of the doors. That's the prize. That's the first step of the experiment. And the second step, you choose one of the doors randomly. And then the final step, which is the most interesting, is after you've chosen one of the doors, let's say you chose door number 1 in this picture, then the host, whose name is Monty Hall, opens one of the other doors, which has a goat uniformly at random. Okay, so you chose one door, there are 2 doors left, at least one of them has a goat. And then the host is going to open one of the doors that has a goat. If both of them have a goat, it's just going to open one of them at random. And the question is, given this information that the host has opened this door, should you switch your choice or not? So any questions about the setup? Okay. So last time we figured out what the experiment, sample space, and event we care about are. So experiment is just this process that generates some an outcome, and the outcome has 3 parts. The outcome consists, the relevant features of the outcome are, where's the car? So that's one of the doors, 1, 2, or 3. which door did you choose? That's one of the doors, 1, 2, or 3. And which door did Monty open? And this is also a door, but it's never the door that you chose, and it's never the door containing the car. I mean, it would be kind of boring if the host opened the door containing the car. So that's the sample space. And the event that you care about is the event that you opened, that you chose the door with the which has the car. Okay, but now we didn't manage to compute the probability of this event because we didn't say what the probabilities associated with these outcomes are. And we're going to do that now. So let's do that. So it'll be helpful to draw a tree diagram of all the possible outcomes. Here's a tree diagram of the sample space. So the experiment has 3 stages. So in the first stage, a car is placed behind one of the doors uniformly at random. So in the first step, I'm going to have 3 possibilities. The first step is the choice of where the car goes. And that could go to door number 1, door number 2, or door number 3. And okay, so these are not yet outcomes, right? Because an outcome is a triple of numbers, 3 numbers, all 3 choices. But if we were to just think about just where the car ends up, what's the likelihood of the car ending up behind any one of the doors? Well, we said it's equally likely to end up behind all the doors. So what's the likelihood that it ends up behind each one?
Third.
Yeah, just a third. So I'm going to label these with 1/3. Okay, and now the next step is that you get to choose one of the doors. So again, there are 3 possibilities. Regardless of where the car goes, you are going to choose door 1, 2, or 3. And you can make all of those choices. And given wherever the car went, you don't know where the car went, and your choice has nothing to do with where the car went. So again, the likelihood of your choice, so this is you, is given where the car went, is also going to be a third. I mean, I'm not making any formal statements about probability yet. I'm just labeling this tree diagram. We'll see how the probabilities relate to these numbers in a moment. And now the last choice is actually the most interesting. So wait, let me move this down so I have enough space. Okay. Now in the last step, the host has to open a door. And the door better not be equal to your door, the door you opened, or the door containing the car. So in this first branch, when the car is behind door number 1 and you chose door number 1, which doors can the host choose? Well, they can't open number 1, so they can open door number 2 or door number 3. And again, the rule is that they choose uniformly at random. So uniformly at random means equal likelihood from all the options. Sorry, that wasn't very good. And so given that the host actually knows everything, the host knows where the car is, the host knows what you chose, but they only have 2 options. And so they're going to choose each of these with likelihood a half. Okay, now what happens in the second branch where the car is behind door 1 and you choose door number 2? According to the rules, what does the host do?
Only 3.
Only 3, right? Because they can't choose the one you chose or the one the car is behind. So they just have to choose 3. And that happens with likelihood 1. And then in the last case, they have to choose door number 2. And then similarly, in the other cases, you get similar outcomes. So in this case, the host has to choose number 3. In this one, they have 2 options. They can choose 1 or 3. In this one, they have to choose 1. And then finally, in this one, they have to choose 2. In this one, they have to choose 1. And here they have 2 options, 1 and 2. So this is what the sample space looks like. Now, in the end, each of these things correspond to points, right? So this is the top branch is the point 1, 1, 2. This is the point 1, 1, 3, and so on, right? This is the point 1, 2, 3. This is the point 1, 3, 2. And then I have 8 more points like that, which I won't write down. But then the sample space is actually these tuples here. Now, what should the probabilities of these outcomes be? So this is not something we've addressed. But what would you? I don't know. What are some suggestions for what this should be?
Maybe multiply together all the numbers along like sort of the sequence of branches leading to that outcome.
Yeah. So the intuition is the proposal is to multiply the numbers along a branch, and the intuition is that, well, these are supposed to be likelihood. So this is the fraction of the time something happens. And so 1/3 of the time you choose a car, then given that, give 1/3 of the time the car is behind door 1, and given that the car is behind door 1, 1/3 of the time you choose door 1, and given that you chose door 1 and the car is behind door 1, half of the time the host chooses door 2. So a natural thing to do is to multiply these numbers. And if you multiply these numbers, you get, let's just label these. So you get a third times a third times a half. So you get 1/18th, 1/18th. And for the other ones, you get 1/9th, 1/9th. And let's just label all of these. So this one, you get 1/9th. So you get 1/18th, 1/18th, 1/9th, and then 1/9th, 1/9th, 1/18th, 1/18th. And you can check that these numbers add up to 1. Now, we will talk a lot about why multiplying is a reasonable idea. So we'll explain why multiplying is justified. But assuming we believe these are the correct probabilities, we can now calculate the probability of this event, the probability that you chose the correct door. So the event, let me just do it with a green highlighter. This is the set of all outcomes where you and the car are the same, right? So that's this one, and then yeah, this one and this one. And then finally, in the last branch, this one and this one. So these 6 outcomes are the ones where you chose the correct door. And so in the end, the conclusion is that the probability of this event is the sum of all these numbers. So it's 1/18 times 6, which is a third. So, the benefit of doing this whole, song and dance with this, writing down the whole sample space and everything that happens, is that now you're sure that even after the whole experiment is over, after Monty opened the door and everything, this is the probability that the car is behind the door that you chose. But then the probability of the complementary event, which is that the car is behind some other door, is 1 minus a third, which is 2/3. So actually, the car is twice as likely to be behind the other door. Now, what was the point of doing all of this? Well, the point of doing all of this is that we broke down this seemingly counterintuitive, confusing situation into something very mechanical using this formalism of sample space, event, probabilities, etc. Right? We broke it down into a bunch of little things that we're really sure about. And then in the end, we just calculated this probability. So any questions about this example? We'll revisit this later using more sophisticated concepts, but any questions about this example?
Yeah, I'm curious if just like the real world data from this game show follows this probability model.
That is a great question. So yeah, I don't know. I'm sure you know, there's a New York Times article about this that somebody wrote a few years ago. I'll send it to the class. There's all sorts of interesting phenomena, sociological phenomena that happen in this game show. So I don't know off the top of my head, but I'll send you this article.
Cool, thank you.
How do we get the 1/18th and 1/9 again?
Yeah, so the rationale was that you multiply the probabilities along every branch. Multiply likelihoods along each branch. So the reason we got 1/18th, let's say in the first example, is a third of the time the car is behind door 1. Then a third fraction of that, you choose door number 1. And then half of the time, given all that, the host chooses number 2. So 112 gets 1 over, gets a third times a half. So yeah, maybe that's what I should spell out. 1/18th is a third times a half. So it's a product of these three numbers.
Thank you.
Yep. Okay, so any more comments before we move on? Okay, so now let's move on to the new sort of higher level concepts. Okay, so far, what have we done? What we've done is something pretty basic. I mean, nonetheless powerful, but basic, which is we've said, well, given, you know, a sample space and some probabilities and an event, you know, how do we calculate the probability of the event? Well, you just calculate by adding, right? Calculate the probability of the event. So given an event E, calculate the probability of E by just adding the probabilities of all the sample points, right? That's, I mean, okay, that, you know, developing this language, it still has some power, but it's a pretty, we're not doing anything very different from counting here, right? I mean, in the end, event is just a subset of the sample space, and where eventually there's just some careful, you know, different notation for doing some kind of counting, possibly with these weights, which are the probabilities. That's not really what probability theory is about. That's what the foundation is, but that's not really what it's about. What it's about is the following question. It's given the probabilities of some events, what can you say about the probabilities of other events? So given probability or probabilities of some events, so here we were given the probabilities of all outcomes, right? Now we're just going to be given the probabilities of some events. Let's say E1, E2 to En. What can you say about probabilities of other events? let's say a probability of F for some other event F. So this F is some other event. So how are the probabilities of events related? That's the real structure of probability theory. So let's develop some tools for relating probabilities of different events. Okay, so first I'm going to develop some very basic, the most basic rule, which is the sum rule, which is not really a new thing. It's something you learned about in set theory. The sum rule says that the probability of the union of two events is the sum of the probabilities of the events minus the probability of the intersection. So this is new, right? In the last lecture, we always just had one event. Now we have two events, right? So for any two events. I mean, okay, this is not surprising. The proof is the same as it was for sets. We won't do the proof. You know, the picture is there's this Venn diagram, right? So there's a sample space. And then there are some two events, E and F. And okay, here you get the idea. Any comments about this? Okay. Important special case of this. If you have two events that are disjoint, then the probability of the union is just the sum of the probabilities. So the Venn diagram associated with this is that the circles don't have any intersection. So these are called disjoint events, just like disjoint sets. Disjoint or mutually exclusive. And okay, an even special case of that is what happens if how is the probability of an event related to that of its complement? In fact, we already used this without proving it. That's just that the probability of an event plus the probability of its complement with respect to the sample space is always 1. Because the union of those things is the sample space, and the probability of the sample space is always 1. So this 1 here indicates the probability of the sample space. Okay. Okay, so now we get to something that's really a lot more subtle. I still get tripped up by it, even though it looks very simple. And this is the notion of conditional probability. Okay, so here's the definition. So the motivation is, suppose you have two events, E and F, and you know that F happened. What does that say about the, how does that change your belief about the likelihood of E happening? So here's the definition. If E and F are events in a probability space, in the same probability space, and F has probability that's not 0, then the probability of E given F. Is defined as probability of E bar F. So this F bar is the given. This is the probability of E intersection F divided by the probability of F. And you can divide by this probability of F because the probability of F is not 0. Very, very important definition. Okay, now what does this mean? Let's draw a picture to try to explain the intuition behind what this means. So you have this big sample space, S. And in here you have two events. You have an event E and you have an event F. And remember, the sample space is a set of possible outcomes. Now, so if you really wanted to follow this intuition, suppose you now know that F has happened in some context. That means that the set of possible outcomes is now restricted to F. Okay, that coloring didn't go very well. Now the set of possible outcomes is restricted to F. So the first step is you restrict. So what's the meaning of this? So one is you restrict the possible outcomes to F. And really what that means is you're shrinking the sample space. Okay, you're restricting the sample space. The possible outcomes is the sample space. So this is like shrinking. And maybe shrinking is not a good word, but you're just restricting the sample space. But then, well, the total probability in F is no longer 1. And in order for something to be a probability space, the sum of the probabilities has to add up to 1. And so if you then rescale all the probabilities by the probability of F, so you rescale probabilities to be 1, then you exactly get this formula. What's going on here is that the restriction is happening in the numerator. You're restricting all events to just be their intersection with F, and the rescaling is happening in the denominator. So that's this intersection is E intersect F. And the probability of E given F is just the probability of that intersection rescaled by the total probability of F. So let's do an example. But any questions about the definition before I do an example? Okay, let's do one example. So let's do this experiment, which is so the experiment is pick a random person in the United States. So then in particular, that means a sample space consists of all the people in the US. Let's say that there are 300 million people in the US. I know there are more than that now, but okay, and let's define two events. So event C or let's say, yeah, let's just call this event, yeah, let's call this event C. Event C is the event that the person is a Cal student. And event B is the event that the person lives in Berkeley. Okay. So now we have two events. So, okay, we need to know the cardinalities of these sets to calculate the probabilities. So let's say the number of Cal students is 30,000. I don't know if that's accurate anymore, but let's say that's what it is. And let's say the population of Berkeley is, I don't remember what number I chose for this. Let's say it's 200,000. And let's say that, so B intersect C is people who are both Cal students and live in Berkeley. So this is Cal students in Berkeley. And this has cardinality, I don't know, let's say 2/3. It's probably a lot less during COVID, but. So given these sets and their sizes and the size of the intersection, I can apply this rule to calculate the conditional probability. Okay, and this is the important thing about conditional probability. Do not try to use your intuition to calculate conditional probability. It's a rule. It's something people have, it's very hard to have correct intuition about it. So let's just do it. So probability of being a Cal student, given that you live in Berkeley. This is the probability of both, given the probability. I mean, to be consistent, let me write it in the same order, actually, although the order doesn't matter. Over the probability of this, and then, so this is, so let's see, probability of C intersect B is 20 times 10 to the 3 divided by the size of S. So that divided by the population of the US. And now probability of B is just 200,000 divided by the population of the US. And of course, the population of the US didn't end up mattering here. And so this ends up being 1 in 10. So 1 in 10 of the people living in the city of Berkeley are Cal students, according to this calculation. I mean, if these are the data. So remember, this stuff is not, this is just given, this is some kind of data that we've got from somewhere, right? This is not part of the content of probability theory. But then the order in which you do this matters, right? On the other hand, the probability of being a Berkeley resident, given that you are a Cal student, okay, follow the formula. And now again, you get 20 times 10 to the 3 divided by the population of the US over the population of Cal students. And this is a third. So these numbers are not the same. The important thing to know about conditional probability is that the event, the order matters, and these are not the same thing. The probability of being a Cal student, given that you're a Berkeley resident, is not the same thing as it's the probability of being a Berkeley resident, given that you're a Cal student. This is a very common source of statistical errors, misinformation in the media, lying with statistics, all sorts of things. So that's the point I want to stress here. Any questions about this calculation?
Could you say again what they calculate?
So what they calculate is, suppose, you mean what is the meaning of these numbers?
Yeah.
Well, the first one is the probability of being a Cal student given that you are a Berkeley student. So in this experiment, we're choosing a random person in the US. And then we're saying, let's assume we picked a person in Berkeley. That corresponds to zooming in the probability space on just the people who live in Berkeley, as shown in the Venn diagram. So the event F in this case is the event B. And then we're asking, what's the probability in that zoomed in part of the sample space? What's the probability that the person is a Cal student? The answer is it's 1/10.
Thank you.
So I often think of conditioning as restricting or zooming in. Zooming in is a good metaphor. Zooming in on a part of the probability space. But it's also the way that we mathematically formalize knowledge, right? So what it's saying is, you do this experiment, you pick a random person in the country. Suppose, if you don't know anything about the outcome, then the probability of being a Cal student. So yeah, for comparison, the probability of being just a Cal student without conditioning on anything is 30 times 10 to the 3 divided by the population of the US, which is 1/10,000, right? So this conditioning is very important. Knowing that the person you picked up lives in Berkeley really changes the chance that they're a Cal student. That's what this is. That's an important conceptual point here. Okay. So that was one simple example. Let me now tell you the second, some immediate consequences of the definition of conditional probability, which are important and have names in their own right. So 2 important consequences.
Professor,
Yes.
I think the probability of B given C is 2/3, right?
Yeah, sorry, you're right. Definitely not 1/3. It's 2/3. Sorry.
Yeah, thank you.
Yeah. Okay. So here are 2 consequences of the definition. So one is the so-called product rule. Now let's look at this definition here. It says P of E given F is equal to a P of E intersect F divided by P of F, right? Well, I can rearrange that by multiplying both sides by P of F. And if I do that, I get what's called the product rule. It says that the probability of E and F is the probability of E given F times the probability of F. This is the second important rule of probability, though it's an immediate consequence of the definition of conditional probability. It's not really a new thing. Now, and this has general, this is sometimes also called the chain rule. And if you apply this fact a bunch of times, you get, so more generally, you can do this with 3 events, right? Probability of E and F and G is the probability of, actually, let's start it. Sometimes it's easier to start it the other way. It's a probability, well, okay, I'll just do it like this. It's a probability of E given F and G times the probability of F given G times the probability of G. And you can do it for 4 sets and any number of sets. And this is really, it's actually the same thing as the product rule in counting. In counting, remember we had this very first product rule. If you can uniquely construct an object using a sequence of choices, and each choice given the previous ones has the same number of options, this is essentially a manifestation of that. But it's an immediate consequence of the definition of conditional probability. And we can now we can explain now a little more formally why we multiplied the probabilities in this example here. Because what were these numbers, right? So this 1/3 here, this is the probability that the car is in position 1. I'm just going to denote that by C1. And then this number here, this was the probability that you chose 1 given that the car is in C1. And then this half was the probability that Monty chose 2 given that the car was in location 1 and you chose door number 1. That was our thought process, right? That given all of these previous decisions, what's the likelihood of these events? And so by the product rule, I mean, it's really a tautology, but I'm just formalizing what we did. The product rule says that the probability of all of these 3 things happening, namely this written here, this is the probability of C1 and Y1 and M2 should be equal to the product of these 3 numbers by the product rule. Any questions about this? So here, I mean, here I'm actually using the product rule in reverse. Here I'm saying that, hey, I know what the conditional probabilities should be. Right? I'm saying I know that the probability of Y1 given C1 is 1/3. That's my modeling assumption. And the product rule is telling me that I should multiply these numbers to get the probability of the intersection of these 3 events. So
I'm one.
Yes?
Sorry.
Yeah, so there are actually 2 ways that the definition of conditional probability comes in. One is, given the probability of an intersection, you can use it to calculate the conditional probability. And the product rule is saying you can flip this on its head. If you know the conditional probabilities, then you can use them to compute the product of the intersection. So that's consequence number 1, the product rule. Consequence number 2 is called the law of total probability. And what this says is if E and F are events, then the probability of E is the probability of E given F times the probability of F plus the probability of E given the complement of F times the probability of the complement of F. And that's it. Let me prove this for you. It's a simple consequence of the product rule and the sum rule. So let's prove this.
Could you explain the vertical line between the 2 letters in probability? How do I interpret it? It's better. Is it like the probability of E that F happen,
No, it's the probability of E given that F has happened.
Oh, given.
Yeah, given. So as you can see in this definition, this is read the probability of E given F.
Got it.
Or sometimes the probability of E conditional on F. Some people say that also.
Thanks.
But I prefer given because it's actually pretty good description, right? Because if you know F happened, then you don't care about the outcomes outside F anymore. So you just restrict the sample space to be F and renormalize, and you get a new probability of the event E, and that's the probability of E given F. So anyway, let's prove this. Well, so the probability of E is the probability of, now it's just set theory. E intersect F union E intersect F complement. So here I'm doing a little Venn diagram thing here, where I'm saying, here's E, and then F and F complement are splitting the sample space into two sets. I'm just saying that, well, E is a union of these two parts, right? This is E intersect F complement. This is E intersect F. Okay. Now by the sum rule, there's a union of two sets. What's the intersection of these two sets?
The empty set.
Yeah, so they're disjoint. So then by the sum rule, you get that this is the probability of E intersect F plus the probability of E intersect F bar, which is by the product rule. Is the probability of E given F times probability of F plus the probability of E, given F bar probability of F bar. And that's the proof. So it's not really a new thing. It follows almost immediately from the sum rule and the product rule.
I had a question about the example.
Yeah.
It seems like it would be possible to sort of figure out what we want to show without computing the probability of the individual events. But I'm worried about, like, do we need to show that, like, do we need to calculate each of those individual, the outcomes, the individual outcomes? Do we need to compute the probability of each individual outcome to show that their probabilities sum to 1?
You mean individual outcomes, like actual points in the sample space?
Yeah.
Well, so I mean, yeah, so we didn't write down a probability here because we're assuming that this random person is picked uniformly at random. So implicitly, what we've assumed here is that the probability of any point in the sample space is 1 over the size of the sample space.
Sorry, I meant to refer to the Monte Carlo example.
Oh, this example. Right. So your question here was do we even need to compute the probabilities in the sample space?
Yeah, and if we don't, is there any way to show that, like, their sum works out to be 1 without necessarily, like, showing without figuring out what each of them are?
It's a great question, and I'll come back to it later. Your question is there a sort of quicker, more conceptual way to do this using these notion of conditional probability? The answer is yes, and I'll do it in a moment.
Awesome.
Yeah.
Thank you.
Okay, so okay, so we've done a lot of these laws now, which may have been a little dry. Let's do some examples. So yeah, so here's an example that comes up a lot. In fact, it comes up a lot these days because everybody, we're taking tests for COVID and things like that, but this comes up a lot in medical testing. Okay, so here's some actual data. So this is related to prostate cancer, which is a pretty common type of cancer. So what are the facts about prostate cancer that I want to use in the example? So there's this disease called prostate cancer. And then there's a test for this called the PSA test. And here are some facts from the NIH. So if a patient has prostate cancer, then the test is positive 80% of the time, and it's negative 20% of the time. Okay, so that means if somebody actually has this disease, the test will detect it 80% of the time, and 20% of the time it won't. So this is what's called a false negative. Another piece of information that has been determined using scientific experiments is if a patient does not have then the test is positive 10% of the time, and it's negative 90% of the time. So this is called a false positive. And then another piece of information that's, of course, all these numbers are approximations because they're determined using experiments, but let's take this to be the model. Another piece of information is that 0.16% of the male population of the US has prostate cancer. So here, these are some facts. Now, given these facts, I want to answer two questions. Question one is what's the probability what's the probability that a random person will test positive? So what fraction of, so okay, I should say, yeah, okay. So before asking these questions, let me define an actually no, this is okay. This is fine. So question one is what is the likelihood of testing positive? So suppose I take the test, what's the chance I'm going to test positive? And the second question is, if I test positive, what's the chance that I have prostate cancer? Okay, so this is an actual thing, but such situations come up in almost any disease where there's a test. And now let's see how to answer these questions using the framework of conditional probability. So, okay, if you're doing probability, there has to be an experiment. What's the experiment here? Well, the underlying population in all of this data is the male population of the US. So the underlying sample space here. So the experiment is choose a random male in the US. Okay. And the sample space is a set of all men, I suppose. And now the events that I care about are C, the probability that this person or the subject, I don't know, the chosen person has prostate cancer. And the another event is that they test positive. Now, given this data from the NIH, what do I actually know? I don't know anything about specific sample points, right? I don't actually have the whole medical records. I have some statistical information. And let me just write down in terms of probability what I know about these events. Let me just move this here. Well, the first data point is saying that the probability of testing positive, given that the patient actually has cancer, is 0.8. And the probability of testing negative, so that's the complement of T, right? T is testing positive, given that the patient has cancer, is 0.2. That's what item 1 is saying. I mean, really, the second line is redundant. Why is the second line redundant?
Because
would it be because we don't care about negative tests because we're only caring about positive cases?
No. We don't know yet. I mean, we don't know yet how this calculation is going to go. Maybe that number will be relevant.
We can just calculate it based on the first line.
How can we calculate it?
Well, the probability is always equal to 1.
Yeah. So the sum of we know that the sum of probability of E and E complement is equal to 1. This also extends to conditional probability. You can just see it from this formula, actually. So, or you can see it from the law of total probability, right? If you just take, let's see, well, okay, you can't see it from the law of total probability, but you can see it from, yeah, you can see it from the definition of conditional probability. If you just add up probability of E bar given F and probability of E given F, you always get 1. Because you just get probability of F divided by probability of F. So a general fact, which makes the second point redundant, is that probability of T given C plus probability of complement of T given C is always 1. Okay, so now for the second information that we know. If a patient does not have prostate cancer, then the probability of testing positive is different. It's much lower. So here we just write that the probability of testing positive, given that you don't have prostate cancer, is 0.1. And I won't write the complementary data because of what's written in the corner. Any questions about how I'm codifying this, this model, really? Yeah, I guess I'll erase this. There's no need to actually write this one. Yeah. And then finally, this is what probability is the last one telling me about? Which event is it giving me the probability of?
The probability of having the cancer.
Yeah, that's just probability of C is, I guess, 0.16%, so 0.0016. Is that correct? Have I put too many zeros there? No, that's correct. Okay, fine. Okay. So now I know these three probabilities. Some of them are conditional. So really, I should have said in the beginning, the new task we're doing is, given the maybe conditional probabilities of some events, calculate the probabilities of other events. So now we're given these three conditional probabilities. I mean, one without conditional. And our goal, so question one is, what's probability of T? And question two is, what's the probability of C given T? So now let's use our laws of probability to answer both these questions. So before I do that, any clarifications about the setup? Okay, so let's do question one. We want to calculate the probability of testing positive. Well, we're not given this information. It's not even super clear we can calculate that information from what we're given. But any thoughts on which of these laws we could use? Could this one be helpful, perhaps? Yeah, because in this picture, what's going on is there's everybody that's split into the events C and C bar, and in here there's maybe I think C is a very small event, so maybe it's not a very accurate picture, but C is some pretty small event, and C bar, and then and now there's this other event T, which I'm interested in. And now I apply the law of total probability. So I get that this is probability of T given C times probability of C plus probability of T given C bar, probability of C bar. Okay, so now I actually know what these numbers are, right? T given C is 0.8. Probability of C is this 0.0016. Probability of T given C bar is 0.1 times probability of C bar, which is very likely, is 0.9984. Okay, so this is just saying that in words, the law of total probability is saying that the likelihood of testing positive is the weighted average of the likelihoods given that you have or don't have the disease, weighted by the probability of having or not having the disease. In words, that's all it's saying. It's saying that you can average the probabilities. You can average the conditional probabilities depending on the probabilities of what you're conditioning on. So okay, I don't really have a calculator. Well, okay, I have a computer, so let's figure out what this is. So it's 0.8 times 0.0016 plus 0.1 times, oh, I didn't put parentheses. Okay. Does my calculator have parentheses? Yeah. 0.8 times 0.016 plus 0.1 times 0.9984. So that's this is 0.110 something. So this is actually saying something that maybe you wouldn't have expected. It's saying if you're a random person and you take this test, there's a close to 10% chance that you're going to test positive. Now you may be alarmed by that, but it's not so alarming because the test has a false positive rate of 10%. So this is similar to the type of, there have been several similar situations regarding COVID testing and vaccination and things like that, which are very easy to misinterpret. Okay, so 10% of the people have tested, are going to test positive. Now let's answer the second question. If you tested positive, what is the chance that you actually have the disease? Now to do the second one, I'm going to, I was going to follow a particular outline, but I think I'm just going to introduce it now. To solve the second part of the question, I'm going to need to use a very important theorem called Bayes' rule, which I'll tell you right now. So Bayes' rule is the more or less trivial calculation that the probability of E given F is the probability of F given E times the probability of E divided by the probability of F. It's extremely important and extremely easy to prove. It's a one-line proof using the product rule. So what's the proof of Bayes' rule? Well, the probability of E intersect F, E and F, I can expand it in two different ways using the product rule. On one hand, it's the probability of F given E times the probability of E by the product rule. On the other hand, I can do it the other way. It's the probability of E given F times the probability of F, also by the product rule. Now you just rearrange. You just move the probability of E given F to the other side. So it's easy to prove, but very powerful because it allows you to reverse the conditioning. It allows you to express probability of E given F in terms of probability of F given E. Okay, so let's use this to answer the second question. I'm interested in what's the probability that I actually have the disease given that the test is positive, right? That was my question number 2. okay, well, let's just apply Bayes' rule. That's the probability of testing positive given that I have the disease times the ratio of the probabilities. Probability of having the disease divided by probability of testing positive. And now I've calculated these before, right? So let's scroll up. Probability of testing positive given C is 0.8. Probability of having prostate cancer is 0.0016. And in A1, I calculated the probability of testing positive. It's about 0.10. So what's the conclusion? Well, this is 0.8 times 0.0016 times 0.10. Which, I mean, okay, I still have that number on my calculator, so I might as well do it. Sorry, I have messed this up.
I calculate to be 0.10112.
Okay, 0.10112. So this is
No, I mean the
sorry, 0.01, right?
no, I mean the PT, not the whole answer.
101.10112, right? Yeah, I mean, I calculated this at home. Let me just see what I got. I got something about 1.3%.
Oh, and the result of P C given T is 0.0127. Yeah.
Yeah, so it's about 1.3%. So what does this say? Well, it says if you test positive, you actually have a super low chance of having the disease. Okay, so this is, I mean, there's a whole thing around prostate cancer that it's the testing is sufficiently misleading that it's sort of over diagnosed and the false positive, basically the treatment is dominated by the false positives. So this is actually very striking because you look at these numbers, right? You say, okay, that looks like a pretty good test, right? If you actually have the disease, 80% of the time it says you have it. If you don't have it, then it only messes up 10% of the time. But that messing up 10% of the time completely ruins the accuracy of the test. So why does this picture, why is this picture not, how do we intuitively think about this picture? Well, let's plot all of these sets on the Venn diagram. Right? So so ultimately the thing that's very important is that the set C, the event C is very small. It's 0.0016. And so what's happening is that the set T is still mostly supported in the set C bar. Or, well, okay, maybe that's not a very good picture, maybe. So, okay, so the probability of T given C, the probability of T given C is large, right? So the set T actually covers a large chunk of the set C. But it actually covers, in absolute terms, an even larger chunk of the set C bar, even though that chunk is a tiny fraction. So what this is saying is if you land up in the set T, you're still most likely to be in C bar. So anyway, I mean, next time you're reading something about medical testing, this is a very important thing to keep in mind. And the thing that really drives the meaning of these kinds of experiments is Bayes' rule. So any questions or comments about this? Okay. So finally, I will tell you a very important concept, which is just a special case of conditional probability, which is independence. So here's the definition. So two events, E and F, are independent if probability of E given F is equal to the probability of E. I mean, okay, let me write the symmetric definition first. They're independent if the probability of E and F is just the product of the probabilities. Sorry, this is times. So this is very important. Now, how is this related to conditional probability? Well, if you plug this into the definition of conditional probability, you get that this is equivalent to probability of E given F is just probability of E. And also equivalent to probability of F given E is just equal to probability of F, assuming that both probabilities are not zero. So this requires that probability of E is not zero. This requires that probability of F is not zero. Otherwise, the conditional probability is not defined. Now, what are the classic example of independent events? You roll 2 dice. Let H1 be the event that the first is ahead. H2 be the event that second is ahead. And now the conditional, well, okay, then the probability that they're both heads. I mean, you can do the counting. If you really do this from first principles, it turns out to be 2/4, which is a half, which is the, oh, sorry, what am I saying? It is a quarter, which is a half squared, which is the product of the probability that each one is ahead. Now, what's the picture associated with this? The picture, so actually, before I do that, let me show you another example. Let's say you roll a dice. Let's say E1 is you roll a 1, and E6 is you roll a 6. Are these events independent? Who thinks yes, who thinks no? Enter in the chat. Okay, so many people think they're independent. Many people think they're not independent. Okay. Good. So, well, let's check. What's the probability of E1 and E6? What's the probability that you roll a 6 and a 1? Okay, so there's a very interesting discussion of false positives in medical tests going on, and I absolutely agree. What I presented is a big simplification. It is true that in the specific case of prostate cancer, there still has not been a very great way to get around it, but I agree. It's really, the real deal is much more complicated. But anyway, what's the probability of rolling a 1 and a 6?
Is this with one die or with multiple?
One die, yeah. Roll
Oh.
one die.
Wouldn't that be 0?
Yeah. So yeah. Okay. So maybe I should have made that clear. So roll 1 die. It's a 0. Right. And so this is not equal to the probability of rolling a 1 and rolling a 6. So these pictures are very different. So these are disjoint events. And disjoint events are never independent if they have non-zero probability. So the pictures are very different. Here, the Venn diagram is something like this, E1 and E6. Here, the picture is something completely different. The picture is that there's a probability space, and there are two different ways to split it. So one is you can split it along H1 and H1 bar. And the other way, which is different, is you can split it along H2 and H2 bar. And what independence is saying is that if you condition on one of these things, so let's say you condition on H1, so you zoom in on this part of the probability space, the fraction of the space occupied by H2 doesn't change. So this is a completely different concept, very common source of confusion here. Probability of H2 given H1 is equal to the probability of H2. So, okay, that's it for today. But really, conditioning and independence, these are the most important concepts in probability theory. And that's what makes probability theory different from counting. It's the concept of conditioning and independence. So anyway, that's it. Today's lecture is this is the last content that will appear on the exam. Everything after today will not appear on the midterm exam. And I will release practice exams and study sheets and so on.
Thank you.
Professor, I have a quick clarification question
Yep.
for the quiz.
Yeah, sure. Mhm.
So this is question 3. So for every element in the domain, like 1 through n, each of those has to be mapped to one of 1, 2, and 3, right?
Well, yeah, I mean, it's a function, right?
Okay, so each of the members of the domain has to be mapped to something. It can't be like mapped to nothing. Okay.
Definitely, because that's the definition of a function.
Okay, I was just
Yep.
checking.
No, it's a good